Hello everyone. This video is for reviewing math problems of KTCE whose employment year is 2024. KTCE stands for Korea Teacher Certificate Exam. Anyone who wants to work at middle school or high school in Korea is supposed to pass this exam. Personally, I think this exam contains many interesting math problems of college level. On this video, I want to deal with analysis problem, which is about interval of convergence of a series of function here. Series of sequence a sub n here under specific conditions. Okay, before I go into dive into the problem, I want to comment about this inequality. This comes from Stirling's formula, which gives us approximation of the value n factorial, which is approximated when n is very large enough. Then n factorial can be approximated to this function square root of 2 pi n times n over natural constant e, each quantity to the nth power. So if I separate the constant part, which is square root of 2 pi, and the rest part is n to the n plus 1/2 power times e to the minus nth power. And since square root of 2 pi is approximately 2.5 irrational value, okay, so this is obviously less than natural constant e, which is approximately 2.7. Okay, so we have upper bound here, e times n to the n plus 1/2 power times e to the minus n here. So this is our right hand side, this part, and this value is obviously greater than 1. Okay, so if I switch this square root of 2 pi with 1, we have lower bound, which is n to the n plus 1/2 power times e to the minus n, which is exactly the left hand side. Okay, let me go into this problem. The second point of this problem is to figure out its recursive formula for the sequence a sub n. We have various methods here. In my case, I want to try the form of what kind of form of a sub n plus 1 with what relationship it has to do with expression of a sub n here. A sub n plus 1 is integration from 0 to 1 minus x squared, each quantity n plus 1 power. But instead of this, I want to write this one as 1 minus x squared times 1 minus x squared and its nth power dx here. Okay, this looks more clear when I distribute each term with the second term here, 1 times the second term and 1 minus x squared times the second term, the second factor, and then we have integration from 0 to 1, 1 minus x squared to the n dx minus integration from 0 to 1 x squared times 1 minus x squared each quantity to the nth power dx. We have this form. So obviously you can notice that the first term is nothing but a sub n here. And then for the first term, instead of x squared, I want to rewrite x times x here, x times x twice, because I want to use integration by parts. So this part has some function that we know whose antiderivative, and the x is some function of u. We don't know its antiderivative, but we do know its derivative. Okay, so let me do integration by part. You can do it by yourself actually. So integration by parts from 0 to 1, x times 1 minus x squared to the nth power dx. This part is some function's derivative, and x part is just some function u, and then we have x times its antiderivative, which is 1 minus x squared to the n plus 1th power. And by taking a derivative, we have a factor minus 2, and times n plus 1 here. So we have this much. X goes from 0 to 1 and minus, and integration from 0 to 1, 1 times 1 over negative 2 times n plus 1, 1 minus x squared to the n plus 1th power dx. So this part is nothing but u times v part, and for the second term is nothing but u prime and v part. The derivative is with respect to x variable. So when we evaluate each term, on the first term, when we plug 0 into x, here we have 0, and we plug 1 into x, here we have 0. So this whole part, first term is nothing but a 0. And for the second term, we have 2 minus sign here, which gives us plus sign. And then we have constant term, which is 1 over 2 times n plus 1. And integration from 0 to 1, 1 minus x squared each quantity, n plus 1 power dx. And as we already know that this integration part is nothing but a sub n plus 1. So by doing integration by part, we get 1 over 2 times n plus 1 times a sub n plus 1. So we have an minus 1 over 2 times n plus 1 times a sub n plus 1. So by arranging each term, you will have a sub n plus 1 equals to 2 times n plus 2 over 2 times n plus 3 times a sub n here. This is our recursive formula, and the constant term here, which is a variable with respect to n, this will be our function of n here. So the third point is to figure out the nth term a sub n here. In the case of our recursive formula here, since we do know the relationship between a sub n plus 1 and a sub n, there's multiplication of function of n here. We do need to know each start term. The first term is a sub 1, so this one is one you can do it by yourself, n equals to 1. By taking a simple integration, you will have 2/3 here. Okay, so we have a starting point, and then we have a relationship with the next term and its previous term that will produce the whole term. So by reproducing this relationship with this relationship, we can reproduce the second term, which is when n equals 1. So we have 4 over 5 times a sub 1, which is 2/3. And you will figure out the rules if you do this trial several times. When n equals 2, and you'll have 6 over 7 times a sub 2, which is nothing but this one. Okay, so we can, by induction, we can induce that the denominator part is a multiplication of even numbers, especially the number of even number is n from 2, 4 till 2 times n here. And then denominator part is a multiplication of odd numbers from 3, 5. The number of odd numbers is also n, 2n plus 1 here. So this is our nth term formula. And to use this inequality, we have to do a little bit massage of this formula of nth term here. We need some numbers factorial here, but as you can see, there's some missing number here, 3, 5, and 2n minus 1, if I say, and there's a missing number 4, 2, 6, 2 times n. If I have those numbers, then I will have, but in this case, I only need the even numbers, set of even numbers for the denominator, and in the numerator I can manage it by itself, because the numerator part 2n times 2n minus 2 times 4 times 2, the number of even numbers is n, and we have n even numbers. We factor out 2 from each numbers, 2 times n minus 1, 2 times 2, 2 times 1, and n factorial. What's left is n factorial here, so the numerator part is 2 to the nth power times n factorial, without any massage here. But for the denominator part, we multiply both sides with by from 2n minus 2 till 4 times 2 here. And this denominator part will be 2n plus 1 and its factorial, okay, here. And as I already did, this is nothing but 2 to the nth power times n factorial. So in conclusion, the nth term of the sequence is nothing but square of 2 to the nth power times n factorial over 2n plus 1 and its factorial. So now we have better form in terms of this inequality. Okay. Okay, to control the term of 2n plus 1 and its factorial, which is denominator here, we just plug 2n plus 1 to n here. So for the upper bound, we have 2n plus 1 to the 2n plus 1 plus half, 2/3, and e to the 1 minus 2n plus 1, which is e to the minus 2n. Its lower bound is 2n plus 1 to the 2n plus 3/2, e to the minus 2n minus 1 here. And we need its inverse, so its inverse will be 1 over 2n plus 1, its factorial, and we take an inverse and switch its position because they are positive, and we have 2n plus 1 to the minus 2n minus 2/3 times e to the 2n plus 1, and for the lower bound is 2n plus 1 to the minus 2n minus 3/2 times e to the 2n. Okay, and we do the same thing for this n factorial part here. And factorial part, we have this one. So in this case, I wanna square of n factorial, and if I use this inequality, and I get the upper bound is n to the 2n plus 1 times e to the 2 minus 2n. Its lower bound will be n to the 2n plus 1 times e to the minus 2n. And if I multiply 2 to the 2n power on each side, and then I will have 2 to the 2n times n factorial and each quantity square. We have upper bound here, is nothing but 2 to the 2n times n to the 2n plus 1 times e to the 2n minus 2. No, 2 minus 2n. I'm sorry. And for the lower bound is 2 to the 2n times n to the 2n plus 1 times e to the minus 2n. Okay, so what you get is, when you multiply those two numbers here, and we get 2 to the 2n times n factorial each quantity square over 2n plus 1 and each quantity factorial. Its upper bound will be, by some calculation, by some cancellations. So this part will give us e cube, and when we factor out its 2n power, then it's some quantity of 2n, and what's left is n over 2n plus 1 and its 3/2 power. And what's inside of this parenthesis is nothing but 2n over 2n plus 1. Okay, so we do the same thing for the lower bound, and they are cancelled out, and there's some quantity to the 2n power here, same power, and what's left is n over 2n plus 1 is 3/2 power, and inside the parenthesis is 2n over 2n plus 1. Okay, by the way, we have an interesting factor here, which is 2n over 2n plus 1 is quantity to the 2n power here. So when I rewrite it as one minus 1 over 2n plus 1 inside the parentheses here, and I take a minus 2n plus 1 power and times minus 2n plus 1 for its denominator, and I take a power 2 times n, and I have the same value here. And when you take a limit, when n goes infinity, if I say, then this fractional part 2n over minus 2n plus 1, it goes to negative 1 here as n goes to infinity, and this inside parentheses goes it converges to natural constant e here, because natural constant, which is irrational number, is limit of 1 plus 1 over sub n, 1 over n, each quantity to the nth power here. So we have the same form here. So as n goes to infinity, this factor 2n over 2n plus 1 and each quantity to the 2n power it approaches to e to the minus 1 here. Okay, so when we consider the convergence of some series, what matters is when it's a trend of each term when n goes to infinity, or when it's large enough. So we need to consider the tail part of a sub n and its alpha power here. So when n is large enough, this term is nothing but a constant, which is e to minus 1 power here. And then for the second term here, I can separate it as n over 2n plus 1 times 1 over square root of 2n plus 1. So when n goes to infinity or very large, the first factor acts like a constant here, and the second factor is what to remain to be controlled here. So to wrap up, when n is large enough, the general nth term, which is 2 to the 2n power times n factorial and its square over 2n plus 1 and its quantity factorial acts like e to cube times e to the minus 1. It's a square of e natural constant times 1/2 times 1 over square root of 2n plus 1. And for the lower part here, by the same logic, we have 1 over square root of 2n plus 1 times 1/2 times e to the minus 1 here. And what point is, what remains to be the function of n is this factor 1 over square root of 2n plus 1. Okay, so the last point, the tail part of a sub n, each quantity alpha power, it goes like when you take alpha power on both sides here, alpha power here. And then we have an interesting inequality here. For the upper bound, we have some constant to the alpha power, which is constant, times 1 over 2n plus 1, and it's alpha over half power here, because there is a square root here. For the lower bound, we have the same. We have another constant to the alpha power times 1 over 2n plus 1, its quantity alpha over 2 power here. So when you make a series here, the convergence of this series is the same of the convergence of the series of 2n plus 1 over 2n plus 1 to the alpha over 2 power and summation n from 1 to infinity here. So alpha is determined by making this series converge to some number, and we do know that by integration test, 1 over x to the, say, alpha power dx, the integration from 1 to infinity, it converges when alpha is strictly greater than 1 here. So this alpha over 2 should be greater than 1. So that means alpha should be greater than 2 to make it converge. Okay, so let me wrap up this problem. So on this problem, we have two parts. The first part is to figure out its recursive formula, which is specific function of n here, f of n here. And then for the second part, we, by taking a appropriate power of alpha on each to each nth term here, and we make a series, it only converges when alpha is greater than 2. And I want to remind you that this whole term is strictly positive here. Okay, so we don't need to worry about a negative sign here. Okay, this is it.